Here's another example based on a graph. This time we have a function, just the graph of just one function, f of x, and its tangent line, y equals x, at x equals 0. So again, we can see that the function's continuous, and so differentiable on that interval. And since it's continuous, the limit as x goes to 0 of f of x is f of 0, and we can see from the graph that's just 0. Also, we can see the limit as x goes to 0 of this denominator, e to the x minus 1, is also 0. So we have the form 0 over 0. They're both continuous functions in the numerator and denominator, so I can apply L'Hopital's rule. Take the derivative of f, and the derivative of that denominator is just e to the x. Now, what's the derivative of f of x at 0? It's just the slope of the tangent line at 0, and the slope of the line y equals x is 1. So this evaluates to just 1 over 1, because e to the 0 is 1. So my overall limit is just 1. Here's an example, give just a function, not the graph. If you look at the numerator and denominator, these are each polynomial functions. They're continuous. So the limit as x goes to 1 of each of these is just found by evaluating each of them. Since the limit as x goes to 1 of this numerator is 0, and the limit as x goes to 1 of this denominator is 0, I can use L'Hopital's. And when I take the derivative of the numerator and the derivative of the denominator and find that limit, I get minus 1/3. So once you determine that the limit is, that you can use L'Hopital's on the limit, it's actually pretty easy if you remember the how to differentiate the functions in the numerator and denominator. There are those other forms that we can use L'Hopital's on. We can turn them into this form of 0 over 0 or infinity over infinity. So if we look at this form, f of x is going to 0 as x goes to a, and g of x is going to infinity. So what does that mean? If g of x is going to infinity faster, then f of x is going to 0. This could be going to infinity. However, if f of x is going to 0 faster, this could be going to 0. So that's why this is called an indeterminate form. We don't know necessarily which function is going to have the greater influence in the limit. So here's an example of an indeterminate product. So the limit as x goes to 1 from the right of ln of x times the tangent of pi x over 2. So it's not a quotient, so I can't use L'Hopital's rule yet, but it is this indeterminate form. So I'm going to rewrite this in a way where I can use L'Hopital's rule. So remembering that tangent and cotangent are reciprocals, I'm going to rewrite this product as this quotient. And then it's in the form 0 over 0. So now I can use L'Hopital's, and I'm going to differentiate the numerator and differentiate the denominator and take that limit. And remember that these, remembering that these are each continuous and differentiable on interval around 1. If I take the derivative of the numerator, I get 1 over x. The derivative of the denominator, I get minus pi over 2 times cosecant squared pi x over 2. And then I can evaluate that limit, and it's minus 2 over pi. So there's some other indeterminate forms that we also can use it on, and that's indeterminate differences. So again, if I have the limit of a difference of two functions and they're both going to infinity, they could remain close enough to each other that one their difference is limited. So this doesn't necessarily go to infinity. It doesn't go to 0, necessarily go to 0. Remember, infinity minus infinity doesn't make sense in the sense of a number. So it just depends on the functions. So again, we're going to try to use L'Hopital's rule by turning this into a quotient. So I'm going to find a common denominator and write this as a quotient. And when I do that, I make sure these are of course still continuous and differentiable. And I need to make sure that they're of the form 0 over 0 or infinity over infinity. which it is. If I put 0 in each of those, I would get 0 over 0. So now I'll apply L'Hopital's rule, and I take the derivative of the numerator and the denominator, and I get e to the x minus 1 over e to the x plus x e to the x minus 1. And again, I end up with 0 over 0. So I can apply L'Hopital's one more time. I mean, you can keep applying L'Hopital's rule. I don't really know if there's a limit. But since this meets the criteria, we can apply it again. My numerator's e to the x. My denominator is 2 times e to the x plus x e to the x. And now that, when I evaluate that at 0, I get 1/2.